Alrighty everyone, hello. Welcome to our last lecture of Micromouse. We'll be covering Floodfill, which is the more advanced algorithm to solve the maze. Did everyone sign in to the lecture today? Alright, perfect, we'll get started. Okay, so just an overview. So we'll be doing, we'll first be going over like the maze design, like how does the actual maze, so we will be competing on actually set up. Then we will go over like maze solving algorithms that we have already done or used in the RAC competition. And then we'll go over what Floodfill actually is, the algorithm itself, starting from like how does it work using pseudocode, and then going over demonstrations so that way you guys can actually work through it, and then as possible different implementation strategies code-wise. So first off, the maze solving that we have been currently doing. So what's the maze and how do we get around? So the maze will be 16 by 16 cells, and each cell is 18 by 18 centimeters. So it's standard, it won't change. This is what it will be on competition day. And you start in the lower left corner, and their goal is a 2 by 2 goal in the center, so it's 4 squares. And historically, and it will continue to be only one way to enter this goal. There'll be only one entrance, something like this. And we need to navigate through the maze with no prior knowledge of its structure before, so that means you can't hard code your mouse. You can't say, oh, this is like the structure of the maze, now just go through it. So literally all you'll know is that it's 16 by 16 and each maze cell is 18 by 18 centimeters. So we've gone over dead reckoning and wall following. So what were those again? So dead reckoning is just where we just continue to go straight until we hit a wall. Whereas wall following, it's where we follow a wall until so we just want to continue following every wall, and then when there isn't a wall, we just make sure to turn in the direction of the wall. Does that make sense to everyone? I mean, this is very just like, either you just go straight until you hit a wall, there you just follow a wall. You pick a wall and you just follow it for like infinite time until you hit the center, hopefully. So dead reckoning only works for like paths and not branched mazes. What this means is that, like, first of all, dead reckoning, it goes straight until it hits a wall, right? So say that there's like a left turn in the middle of that straightaway, then it will never ever take that left turn, even if that's the way to solve the maze. So therefore, it only works on paths and not branched mazes. And then wall following only works for simply connected mazes. What this means is that there's no loops. Like, you can mathematically prove this if you wanted to. But our mazes are designed such that neither of these methods will work. So if you try and run these two methods, you will never solve the maze. So, and there's also like a random thing you can do. So like you can just be like, at every cell, be like, okay, pick a random number or pick a random direction and just choose that direction. That is very inefficient. You might be able to solve the maze, but it'll take like, you'll probably exceed the time that you're allotted to solve the maze. And then there's this algorithm, where like you can just mark I'm not going to try to pronounce the name, Micromouse algorithm, and basically you just mark which cells you visited, which cells you haven't visited, and although this will actually allow you to solve the maze, it will not guarantee you the shortest path, because you'll just be going from cell to cell and not have actually any sort of sense of which is the optimized path. And now, this lecture we'll go over Floodfill, which is, it will allow you to guarantee the shortest path after doing several runs of going through the maze. So I know this is like a lot of different approaches, but are there any questions regarding these approaches? So these are all not optimal. This is the optimal one that you want to use. Are there any questions? No? Alrighty. Okay, so.
Okay, so now we'll get on to kind of an overview of what Floodfill actually is. So the high-level idea of Floodfill is that you can think about it as if you're trying to go from the goal to the starting point. And basically what you do is like, you just pour a bunch of water at the goal, and based off of what path the water will take to the starting point, that's always guaranteed to be the shortest path to the start. So the goal is to find a path between the start and the end point, which you can just like determine by yourself. And the working principle is that like you're literally just pouring water at the goal and seeing where the water goes to get to the start. And like the water will obviously keep flowing around the different walls until it eventually reaches the starting point. And intuitively, like the path that the water takes is going to be the shortest path. this might seem a little confusing right now, but like we'll get into the specifics very soon. So before we get started on like the actual Floodfill part of it, let's first discuss Manhattan distances. So because we are trying to solve a maze and you can't really go diagonally through the maze, well, you can, but like for like the purposes of trying to find the shortest distance to the maze, we're just going to be using Manhattan distances, which are basically the amount of moves that it takes to get from one point to the other. So if you look at this diagram over here, assuming that the x is the goal, we've numbered like the rest of the squares based off of how many moves it will take your mouse to get to that x, starting from any square. So for example, if it starts from this square right here, it'll take the mouse 3 moves, 1, 2, and 3 to get to the goal. And yeah, this is given that your mouse can't travel through the walls. Yeah, so the basic idea is that you want to have like a map in your mouse of like the maze and all the Manhattan distances in the maze. And like if the mouse knows where it is at any given point, it can always move towards the smaller numbers such that like it'll eventually get to the goal. Does that make sense? Okay. So we could just like go through like a small example of Manhattan distances over here. So like let's say you start right here in the bottom left and the goal is the x. The reason why, or like what you would do is, okay, the mouse knows that it can move right or forward, but it can't really move right because there's a wall, right? So it'll try to go towards the next smallest Manhattan distance square that it can go to, which in this case is 8. So it'll just like move forward to 8. And then it'll look around it again to see what squares it can possibly go to and pick the smallest one again. So in this case, it can go back to 9, it can go to this 9, or it can go to the 7. So the optimal move is to take a right and then go forward to the 7. And if you continue doing this through the maze, you'll see that eventually you will reach the center in the fastest way possible. Does that make sense to everyone? Okay. So, so for like the Floodfill for the mouse, this is like the pseudocode for the overall algorithm. Basically what you want to do is you want to start with the assumption that you don't know any of the walls. So basically your Manhattan distances will look like these, no matter what at the beginning. And the reason for that is because the mouse doesn't actually know that any of these walls exist at the start, so it just assumes that there are no walls. And then essentially what you do is at the beginning you just use Floodfill, which is the algorithm that calculates these distances to like fill your entire like maze in your mouse's memory with like the Manhattan distances. Then what you want to do is you want to travel towards the decreasing numbers, like we've discussed just now. And then as you keep going through the maze, what you want to do is you want to update the walls that you've seen. So for example, if your mouse starts going forward this way, it'll see that there's walls to its right, and so it should like update those walls in its own memory. And then if your mouse ever gets stuck as it's going towards the lower numbers, you want to recalculate Floodfill with like the walls that you have now discovered, so that it will like recalculate the Manhattan distances and take the new optimal path from there. And basically what I just said is like written here. As you get stuck, you just want to keep recalculating the new Manhattan distances using the Floodfill algorithm. This might seem a bit confusing. Does anyone have any questions? Okay. So now let's go through an example. So let's say the arrow is the mouse and you're going through the maze. You start in the bottom left. And since like the mouse can see that there's a wall to the right, it's trying to get to the center and trying to go to squares that are that have less Manhattan distances than the square that it's currently at. In this case, it would go forward to square 3. Then it'll see the wall to its right again. Note down that wall is a known wall, and it'll keep going towards the lower numbers. So it'll still keep going forward to 2. And then it'll see the wall, but it doesn't really matter because even if the wall wasn't there, it would still try to go to the next closest or the next smallest Manhattan distance, which in this case is to its right. And then eventually it'll reach this scenario where the mouse is stuck. So in this case, what you want to do is, now that the mouse is stuck and it can't actually get to the goal, you recalculate the Manhattan distances using the Floodfill algorithm. So you perform Floodfill again, and this is all done with like a function call in your actual mouse. But when you recalculate Floodfill with the known walls, you will get the maze to the right with the new updated Manhattan distances. And then you basically just keep repeating this process over and over again, and eventually you will reach the center of the maze.
And theoretically, you could, if you wanted to, recalculate the Manhattan distances after every single move. But there's no need to, as Parth said, because the only way you will get stuck is if there's a wall that's obstructing your next move. So you can just do it whenever you hit a wall that obstructs your next move.
Okay, so now let's go through like the Floodfill pseudocode. So far we've been discussing like the entire algorithm. Now let's get into the actual Floodfill part of it. So this is like the code or the pseudocode that you would use to calculate the Manhattan distances. So what you would do is, so first of all, this is a breadth first search algorithm, and it uses queues to determine, or it utilizes queues to find the Manhattan distances. We'll get into what queues are and how to implement them in C a little later on, but essentially all you need to know is that it's kind of like a line where different squares or objects or different anything really can enter the line, and whoever enters the line first is also the one that leaves the line first. So what you start off with is that you set all of the cells in your maze to blank, except for the goal, which you set to 0, because the Manhattan distances from the goal to the goal is just 0. So you set the goal cells value to 0, and then you add the goal cells to the queue. And basically what you want to do is that while the queue is not empty, you keep taking squares out of the queue, and then you look at the squares that are next to the square that you took out of the queue. So for example, if we go back to this example, we set the goal square to 0, and we add it to the queue. And then, since the queue isn't empty because it still has the 0 square in it, you take it out, and then you look at the squares that are around the square that you currently took out of the queue. And then you basically just add 1 to the current Manhattan distance, and then set that as the new Manhattan distances for the squares around the square that you just took out of the queue. And then you add all those squares back into the queue, and you basically just like keep repeating this process. So essentially what this is doing is that as you're calculating Floodfill, you are like marking all of these squares as done, and then adding them to the queue so that the next level of Floodfill can be calculated. So, for example, if I use the square 0 and calculate the Manhattan distances for these 3, I would then use these 3 squares and calculate the Manhattan distances for its neighboring squares, and so on and so forth, all the way until you reach like the corners of the maze.
And I don't know why Parth didn't refer to like the 4th square, the one where the 1 is. Like why are we, if we look at this, if we're taking this square out of the queue, we're looking at these 3, but why are we taking this one into account also to add to the queue? So if we go to the next slide. So yeah, so the thing is we're taking all blank and accessible squares, or accessible neighboring squares into account to add to the queue, and if we look back at that maze, we can see it isn't accessible because there's a wall right there. So only these 3 are accessible from this square, and this one isn't because there's a wall.
Okay, so now we'll go into like a demo of what Floodfill would look like.
Okay, I'm gonna switch to my iPad because there's a whiteboard behind this. So I can just... Okay, so I'll be relying on your guys' engagement to go through this. Alrighty, let's see if this loads up. Sure. Okay, perfect. Okay, so this is just like the raw state of our maze. So imagine each cell. So each cell, this is like a smaller maze again, and we're just only having a center square as our goal instead of 4 cells, but this is just a demo anyways. And then why do we know that these, and why are these outer walls already solidified as known? It's because like we know this is the size of the maze, and that's why we can like already say, okay, there's a wall here, 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 and all going all the way around. Is because we know the size of the maze, and then we already know that this wall exists because our mouse starts off in that position. And also like for every single maze, there will always be a wall to the right of the Micromouse when it starts. So we already know this initial setup. There'll be a wall to the right, and then there's walls all around surrounding the maze. So now let's. So we take our first step where we set all the cells except our goal cell to 0. And then now we add our 0 or goal cell into the queue. We remove from the queue, and then now we are in this step where we want to set all blank and accessible neighbors to the front cell's value +1. And take into account that the only walls we know are the outer walls plus this wall. So we don't even know that these blue walls exist yet. The mouse, well, maybe we know, but the robot itself does not know. So who wants to come up and tell me what numbers would go in here, these 4 cells?
Actually, let's just do the first one for them, and then they can come up after that.
Oh, sure. Okay. So, alrighty, let's do this. So again, so we want to set all blank and accessible neighbors to the front cell's value +1, and since sure. So, okay, sorry. Give me 1 second. I'm gonna turn on. Okay. So we first add. We had 0 in the queue, but then we removed it from the queue, right? So I'm taking that next step of like where we already removed 0 from the queue, and so we can add. Oh yeah, I don't have the queue first. Yeah. So I'll first set this one. Oh, I'll set this to 1, this to 1, that to 1, and that to 1. Does everyone understand why? Because again, like we don't know that these walls right here exist. And then there's no wall right here anyways. So that's why, and from the mouse's point of view, all these 4 cells are accessible from the center cell. And then now we can just add these processed cells to the queue. Because we added those 4 cells, and these 4 cells are not added to the queue. And I'm taking into account that they are separate objects, so like, just for clarity's sake, I'll do this. Like they're all different separate cells, right? It's not like I'm like duplicating 1 cell 4 times in the queue. They're all separate cells that I just added. Okay, does everyone understand that? Oh.
Yeah, so when we implement this and we actually have a queue in our program, would the things we push onto the queue be like coordinates of the positions of places where we just processed?
Exactly, yeah. So you would have like a square. So like each object you put in your queue. So at least how I did it was like a coordinate. It was like a struct with like, it stored the coordinate of that cell, and then it also stored the Manhattan distance. That's how I did it. I'm probably not anything to that, or?
Oh, no, I think that's perfect. You could just store the coordinates of each of the cells and like, as a struct object, and then just like add the objects to your queue.
Yeah, exactly. Well, we're not done yet though, right? We want to do a whole entire run through of this. So what do we take out of the queue? Which one do we take out of the queue? Do we take out this one, or this? Which one? Yep.
1D.
No, so remember in a queue we take out the front object, right? So it's like a line.
No, so it's not like what you put in first, you take out?
Oh, it is. Oh, we put in, oh, okay, I put in 1A first.
So you put it in from the back? Is that what you're saying?
Yeah.
Okay.
Yeah, okay, yeah, sorry. Yeah, so basically like how it works, I mean, I just re-clarify how a queue works again, just in case. So basically how a queue works is whatever object you add, you remove objects in the order that you added them, right? So if I added 1A first, that would come out first. B would come out next, C would come out next, D would come out next. So they come out in the front of the line. So basically it's just like a lunch line, from like high school, right? Whoever's in line first gets food served first, and they're taking out the queue out of the line. So 1A will be taken out first. So now let me take out 1A. And now I'm taking 1A into consideration for this entire loop, right? So who can tell me what these, okay, actually, I probably shouldn't say. Which cells should be accounted for? If does anyone want to come up, actually, that'd be great. Just for 1A. Perfect. Okay. So fill in the cells.
Wait, wait, can I random? Wait, no, right?
No, right.
Yeah, I'll flip it, yeah. Yeah, okay. Wait for 1A?
Yes, for 1A. Oh. Perfect. Exactly. There you go. So does everyone understand how this worked out? All right, perfect. So yeah, so now we just add again 2, 2, 2, and we just do the same process for 1B, 1C, and 1D. So that's actually, so now we're on 1B. So do I have to overwrite this too? I mean, okay, it would result in the, it would allow us to have the same result. But is there any necessity to overwrite the 2? Well, actually, I think that's a bad way of putting it. We shouldn't overwrite the 2 because say that this was, actually we'll get there, sorry. So we don't have to, we don't take this 2 into consideration for when we're taking 1B's neighboring cells into account because it's already filled in. Oh, actually, it's a perfect example. So we're on 1B, right? And 1B's neighboring cell also is the goal cell, correct? So does that mean I overwrite the goal cell and put in 2 here? No, because then not only do I like destroy the point of like the goal of the maze, but also I'm increasing the path, which has already been optimized. I think it would make more sense when I go further more cells in, but you only want to set the cells that are blank and accessible. So yeah, so that's exactly correct. This will become 2, then this will also become 2. I'm not going to fill in the cube because it's going to get too long. It's like we're going to exceed the length of the cube, but it should hopefully make sense. So that'll be 2, 2, 2, and 2. Okay. So now, does anyone else want to come up and do maybe this one for me? Any volunteers? Perfect.
I also have a question, which is
yes.
when we're implementing this, how do we figure out how long the queue needs to be?
Well, you know that so okay, that's a great question. Is that
We'll get into like the queue implementations a bit later.
Sure, yeah. But maybe keep it in mind. The hint is it's a fixed size maze.
So we're looking at the underlined one, and it
yes.
has 3 neighbors, and only the 2 above and below are blanks.
Perfect.
So we'll just write 3 there.
Exactly, there we go, perfect. Yeah, and then I'm just gonna go ahead and just fill in the rest for time's sake. So this would be 3, 3, 3, 3, 3, 3. Yep, okay, perfect. And then now we can just take those, and again, remember each time I'm writing a number, I'm adding that to the queue. And then each time and then for example, so at this stage, what we now see in the queue is something like this. So I had the 0, and then I had 4 1s, and then I had 4, 5, 6, 7, 8. Okay, I'll just say 8 times 8 2s, and then I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Yeah, 8 3s. And then I only ever analyze the squares with a Manhattan distance of 3 once I finish analyzing the neighbors for the cells with these following Manhattan distances. Does that make sense? So, yeah, okay. So after I do the 3s, now I move on to now that at this point, after I've added all the 3s to my queue, I finished processing all of these cells because I've removed them from the stack. So in order to get these cells of Manhattan distance 1, I had to remove the 0 cell from the queue and analyze its neighbors. To get the cells with the Manhattan distance of 2, I had to remove all the cells with a Manhattan distance of 1 and analyze their neighbors. And then subsequently I remove all of the cells with a neighbor of 2 to get the cells with a Manhattan distance of 3. Sorry. Does that make sense? Okay, perfect. And that's why it's a breadth first search, right? Because we're going incrementally 0, 1, 2, 3, 4 up to the biggest number, instead of going from 0, 1, 2, 3, 4 and then looping back to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That would be a depth first search, which is not what we want. Okay, I'm just gonna finish this off since everyone seems to get the point. So this would be 4, 4, 4, 4. So can anyone tell me what the path would be for the Micromouse right now? Okay, it's pretty easy enough. You just go this way and you just go this way. So because it is follow again, as Part said earlier, you just follow in the direction of the lowest Manhattan distance. Okay, that brings up a good point. Say there was like a no wall. Say there's no wall right here hypothetically. You can just choose other. I can choose other path. It is up to your preference and your coding. But since there is a wall here, it has to go here, 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 and then here. But then as we'll see, well, okay, so this is like the these are the Manhattan distances that we just discovered up here. But then womp womp, we hit a wall. So now we have to redo our Manhattan distances. Does anyone want to speedrun it right now? Okay.
Wait.
And preferably, try to explain it as you're doing it, so we know your steps.
Okay.
Also try to do it like with the cube.
Yeah, try using the cubes.
Oh, okay.
Yeah.
So it starts off just like as we did last time, where it's like there's one, and then there's. Should I do this?
No, you don't need to.
You don't have to do that. It's fine.
And then does that.
Mm-hmm.
And because we don't know that wall is there, we keep going, but we don't do the one that the mouse is currently on because there's a wall there that's inaccessible.
It's inaccessible because there's a wall there.
Yes.
Yeah.
And then it would do this.
So what did you do for that step? You removed one from the stack, or from the queue. Sorry.
Or what? Oh.
Which cell did you move from the
I
queue?
removed this from the cube.
Perfect.
So I removed that one because it just populated that one, and then you just keep going around.
So now the new cell that's in the front of the queue is this one.
Yes. I think we'll do that. And then now we'll do these two. We'll take this off the queue. We don't do a repeat because that's already been added. And then we just keep going. I'm just not going to do the queue because it's going to take too long.
Yeah, so you can just remove that one just for the sake of clarity.
Yeah. And then, oops, my bad, I can't. That's
Okay.
a 4.
That's okay,
Four.
I got it.
That's a 4, guys. That's 4.
Yeah.
Yeah. So 3, 3, 3, 3. This is also technically a 3.
Good.
And then 4, 4, 4. Technically, we don't need to do those because the mouse will never go there because it's too far away.
We're not done yet.
Yeah,
We're
just-
Yeah.
Finish the rest of
finish
it.
those
Oh.
nice.
That's true. That's true.
4. Oh.
Oops, sorry. I started counting down.
Perfect. Oh. There we go.
There you go.
Perfect.
Okay. I can count.
Does everyone understand how he did that?
I can count.
Okay, yeah, so does everyone understand how the queue portion of this whole thing works? Okay. If I can go over the queue again if anyone needs help with that. But okay, don't be shy to ask, please. Like this is why we're having this lecture. Okay. So now if those distances were correctly calculated, so these will be the Manhattan distances now that we have for our maze. Oh, and if you're wondering, like, where exactly do we store these numbers? It would just be in some array. If you're trying to like, conceptualize it that way, it would just be in some sort of array that stores all these numbers. And then now we want to move. Okay, so now we want to go in this following way. So we're on this cell right here. We could either go down, or we can go this way, or we can just go this way. But in our implementation, we just have it go up. 3 or 1, we want to go to the 1, and then 1 or 0, we want to go this way. But again, womp womp, you have another wall. And we can't go right and then go to the 0 goal. So I'll just do this portion myself for the next set of Manhattan distances. And I'll actually try to use the queue better this time. So we're starting from 0. We're starting our calculations from the center goal, 0. And we take in the accessible and blank neighbors, which are only these 2 cells, and we add those to the queue. Then I take into account, and then I remove this from the queue, and I take into account its neighbors. So let's say that cell corresponds to this one right here, and its blank and accessible neighbors are these 3. I remove this, and then I add these to the queue. Then I look at the next one, and I add its blank and accessible neighbors, and those of that. Now I can finally look at the 2s, or the cells with the Manhattan distance of 2. So I'm going to move this one from the queue, and let's say that corresponds to this one right here. So now that's 3 and 3. Then this one is, oh, I missed one, didn't I? 1, I did. There we go. Oh yeah, right. Sorry. Yeah, thank you. Sorry, my bad. So now that corresponds to a 3 and 3 right there, and then I did two cells of Manhattan distance 2, so that's also 3 and 3 right here. And then now there's this one, so I'll move that one, and then that's just, and then there's only one blank cell, which is to the right of it. So I write a 3 over there. And then now I have these two remaining cells. For this one, there's only one blank cell that neighbors it, and that's the one above. And then now similar thing for the last one, and that's a 3 right there. And we can't do the one to the left, of course, because there's a wall that we have not discovered. Oh, and I forgot to add all these to the queue. My bad. Sorry. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So as I was writing all these 3s, I should have been adding them to the queue, and that's my bad, sorry. So imagine that as I was writing each 3 on the grid, I was also writing the 3 in the queue. So now I take the 3s out for consideration. So now let's say that 3 corresponds to this 3. So that's 4, 4, and because those are the only accessible cells, only blank and accessible cells that neighbor that 3 cell. And then similarly, okay, I'm not gonna add to the queue. I guess I could. Why not? Yeah, I'll just finish it up. I think you guys get the point. So there's 4 and a 4, 4, 4, 4. Those are all the 4s. Then I do 5, 5, 5, and then 6 and 6. And you want to keep on going until you populate the whole entire maze and all the gridded cells. So even like, say you even hit, I mean that's how your algorithm will work anyways, regardless, because it doesn't exactly know where your starting spot is. Because like so this Floodfill, so even if your starting spot was over here, it would still work to populate the entire maze with Manhattan distances. Okay.
And the reason for that is, like Arunan said, because like we're using while queue is not empty as our break condition for the while loop. So as long as there are more squares will keep being added to the queue, so the queue won't be empty until all the squares are processed. Question?
Yeah, wait, what's it called? Wait, beforehand, like when it takes like the most optimized path and it hits here, it detects all these walls, right?
Yes.
Yeah.
Okay, but then wait, how does it detect that one?
Because as we're going up, so the things we were here, right? The previous time we were just, okay, I'm recording this spot. Okay, perfect. Yeah, so we were just right over here, and then
I'll look more.
Okay, perfect. Yeah, so we were just right here.
Yeah.
And then now we know that the next optimized path is to go this way.
Yeah.
But then as we're going this way, at each and every single cell that you get to, you want to record the mazes. So you want to record the walls that are around it. So every time you get to another cell, you want to record the walls that are around it. And then hence why we know that this wall is here and that these 3 walls are here.
I see. Okay.
But then we only do the recalculation of the Manhattan distances once we get stuck at a point where we can't get to the next cell that has the next lowest Manhattan distance. Does that make sense?
Yeah.
So you only recalculate the Manhattan distances when you can't go to the next cell with the lowest distance.
Like, why would you recalculate the one, or why would you populate them if they're like greater than the one, greater than or equal to? They have a greater than or equal to Manhattan distance than your current square.
Take it?
Yeah, so the reason why you would just like populate it is just because of the way that the algorithm works. Like you're not, so like the entire Floodfill part that we're doing right now, where we're calculating all the Manhattan distances, is done through this like general algorithm, right? And this algorithm will keep going until the queue is not empty. So it doesn't really care about where your mouse is. It kind of just keeps going until it gets like to the entire maze and then it stops, if that makes sense.
Well, I mean, like, could you just add a condition that if you take out something from the queue and it's the same number, or it's greater than a number you're adjacent to, you would just stop or something like that?
You could do it, but like something to keep in mind is that when you're calculating the Manhattan distances like in code, right? You're rewriting the entire array that stores the current Manhattan distances. So like if you wanted, you could like copy them over and then like stop after a certain point, but like that's just going to end up making your algorithm slower than it would be if it just like continued calculating the rest of it.
I mean, like, what if you just left them blank? I guess.
Oh,
'Cause then, I mean,
okay, yeah. Actually, you could leave them blank, but like, the reason why you don't want to is because like, you still want to know what all the Manhattan distances are when your mouse is coming back to the center, or like back to the start, or like doing
what if you
subsequent
like, do it at
runs.
the end, like when you're in the goal, then you calculate the whole thing.
I mean, yeah, you could do that, but like,
I think one more thing I want to add is in this scenario, the most optimal path perhaps is like this way. But just because you get to the center in your first run doesn't mean that that is the most optimal route. And having those other Manhattan distances will allow you to calculate more optimal routes on future runs. Because from a few slides from like a while ago, it said that Floodfill will find the shortest route after multiple runs on the maze. And you have to take that into account because again, it will only, maybe in the first one, yes, in the first one it will definitely get to the center, but it may not be actually the shortest path. And that's why you want to come back to the start.
no, he's saying like, what if you you just ignore these three, right? Until
Yeah.
you get to the center, and then when you get to the center, you calculate everything.
I mean, yeah, I guess, but like,
I mean,
That's
is this very expensive? Like, is it quick?
Well, you know, it's very quick.
Oh, okay.
Because
So
the
then-
maze
can't
is only
notice it.
16 by 16, right? It's not like millions of squares long.
it's like order one if you want to think about it that way. Like yeah, it's very quick. Like I've run this in the simulation, like in the assignment you'll have run a simulation of Floodfill, and like it recalculates Manhattan distances like instantly fast, very fast.
I think like just to add on that, like you could implement Dijkstra's out, like what Google Maps uses or like just GPS, but like it's 16 by 16. That's overkill. We have 100 megahertz on the nuclear boards we're working with. We have enough computational power. It's fine.
Yeah, you don't really need to worry about like the speed of the microcontroller. It's been tested with like really bad implementations, and it like still works perfectly
Yeah.
fine.
It can be very unoptimized and it'll still work just fine. You can zip a lot of memory and it'll slowly just be just fine.
How could you like record a wall like in code?
Yeah, we'll get to that a bit
Oh,
later.
okay.
Yeah.
Okay. Again, we're stuck over here. We start moving this way. Okay, so we recalculate the distances. We get to this cell right here, and then we can't move to this one. So then we recalculate the distances again. I'll just show them to you because you guys get the point now. So now the new optimal route is to go like this. Oh, sorry, no, my bad. Is to go like this. But then again, we see that there's a wall that's obstructing our path to just go up. So we recalculate. We get this. I was like, oh, we can go this way, but it's like, there's another wall there. God damn it. And then, sorry. And then, so now we finally realize, oh, we have to go all the way around. And then now that's what we do. And now we're at the center. Yay. And yeah, and then now these are the final Manhattan distances. So if you were to start from the beginning, say we somehow teleported back there. I'm just saying, no. What actually happens is you can recalculate. Actually, we'll get to that in a little bit. But now that we have these Manhattan distances, we can now know that the optimal path is this. And possibly, actually the only path also for this maze. Okay, now we'll go into implementation tips. Any questions though, really quick, before we move on? Any questions on the demo? Alrighty.
Okay, so now let's go into like one of the questions that was asked earlier, and that is how we actually implement the queue in C. So just a quick recap, a queue is first in, first out, or FIFO data structure. And what this basically means is that you could think about it as kind of like an array that keeps growing and shrinking. And the way that it grows and shrinks is when you add things to it and when you pop things for it. So when you add things to the back of the queue, that's called an enqueue or a push. And then when you take items from the front of the queue, that's called a dequeue or a pop. So moving on, there are several different ways to implement queues, but like the two main ways that queues are implemented are through a circular array or a linked list. And we'll go through both of these. And like some of you might have like taken CS32, and you guys are probably just like, oh, well, why don't we just like import the queue library or something, right? So in CS32, you guys used C++, unfortunately, C doesn't have like its own built-in. Well, not built-in, but it doesn't have like a standard Q library to it. So you're gonna either have to build it yourself, or what is more popular is you could just like find a Q implementation in C already that's like online, and then you could try to use that as well.
Who hasn't taken CS32 yet? Okay.
Taking it right now.
Okay.
Okay, then it's probably fine.
Yeah. Yeah. If you need help, just like let us know.
Okay, so wait, actually, can we do it?
Oh, you with your laptop?
Yeah.
Yeah.
Okay. So, let's move on. Okay, so the first way that we can implement a queue is with a circular array. And what a circular array is that it's basically a big array, and you just have two pointers pointing into the array that denote the start and the end of like the actual data that you care about in the array. So, in this case, start would be the pointer that points to the front of the queue, and end is the pointer that points to the part of the array that's like immediately after the last object in the queue. So in this case, this cell would denote like the first object in the queue, then this would be the second, third, and fourth. And then when you want to push things to the queue, essentially all you do is you would follow the end pointer and just like fill in whatever data you want to fill in, and then just increment the pointer to the next empty space in the array. And then like we're just going to add a couple more objects to the queue. Something that you might notice is that the array isn't actually circular in memory. So what would happen is that a lot of the times if you add a bunch of objects, you're eventually going to hit the end of the array. And if this happens, all you need to do is just reset the end pointer to the start of the array. And then to pop things from the array or to dequeue them, essentially all you need to do is keep moving the start pointer to the right. So you just keep incrementing the start pointer. And yeah, essentially what this does is that you now have a new front of the queue. Does this implementation generally make sense to everyone? Are there any questions?
You want to, like, before you move the start pointer to the right, you want to read the value that's in there and then move it to the right.
Okay. And we're just gonna do that one more time. Okay, so the second way to do, to implement queue, oh, actually, before we move on, something to keep in mind about this specific implementation of the queue is that it is technically limited sized. So, like, you might notice that this can only hold like 8 objects, right? It might be a problem, however, we do know that the maze is 16 by 16, so it can only have a max of like 16 times 16 items in it. So you could just like make the array large enough so that it never actually encounters that problem.
So there's 256 elements is enough.
So the second way to implement queues are with linked lists. So a linked list is basically a fancy data structure that has a bunch of these nodes, and the nodes just have like the value that it stores and a pointer that points to the next node in the list. And in this case, what you would do is that you just have a head pointer that points to the front of the queue or linked list, and it, like in this case, it would just point to this this node right here, and the very last node in the list would have a null pointer, and that's how you know that you've reached the end of the list. In this case, if you want to enqueue or add things to the queue, you would just like create a new node, and then make the next pointer of the previous node point to the new node that you just pushed to the queue. And you would kind of just keep doing this over and over again until you want. And then to remove things from the linked list queue, essentially all you have to do is move the head pointer to the next object in the queue, and you know where the next object is from the current head's next pointer. So basically, you would just set head pointer equal to next pointer, so that this will also point to the next node, and then you would just delete the node that you want to use. So that's essentially what it would look like if you pop items from the queue, and you could just keep doing this. Actually, before we move on, does anyone have any questions about the linked list implementation of the queue?
The big difference from a circular array also is that a circular array is defined its size at compile time. So if you set it to be 256 elements, it will be 256 elements no matter what. But with a linked list implementation of a queue, it could be a variable number of elements long, because to create each and every single node that you just saw, you have to allocate new memory using dynamic allocation to create those new nodes. And that's like the biggest difference. Like, do you want to deal with memory allocation, or do you want to deal with like a fixed size array and just move pointers around in a circle?
Can we do better than 256 for the circular array?
I mean, yeah, you could do whatever you want. You could probably store like thousands of.
I mean, can we have a queue that's shorter than 256 in elements and get away with it still, no matter what the maze configuration is?
Probably.
But
I mean, like you're not really saving anything. You're saving like barely any memory by doing that.
I know it doesn't matter much, but 256 seems like a lot, because if you use that many, you're never actually circling around in the array, because you're only going to ever push 256 things to the queue.
yeah, you're right. I mean, technically, you could. Okay, so if we go back to the actual maze layout, all you really need is like enough to store like this diamond that's created by like connecting the centers of each of the sides. So in this case, you only need 8, or like an array of size 8, because at any point not 8. 8 plus what? Okay, so you only need like 2 layers of storage, but like you could technically like make it less, but it doesn't really matter because we have plenty of storage in our microcontrollers. Does anyone have any other questions about this? Okay. Moving on to some other tips. The first one was already mentioned, but basically to keep track of your coordinate system, or like each of your cells, you could use a struct, which is just like a fancy, or not a fancy, like a less fancy class in C. But yeah, this could store like the x and y coordinates of that particular cell, along with like the Manhattan distance, like Arunan said, or actually, yeah, that's basically all you need for each of the actual objects that you're using. And then another implementation tip that might help is that to store the actual walls, you could do it in 2 main ways. The first way that you could do it is by having like 3 different arrays for the maze, where one array represents all the horizontal walls in the maze, one array represents where all the vertical walls in the maze are, and then the last array represents the Manhattan distances. Or you could do it a different way, where you just have like one 2D array, and you like number each specific configuration that each square can possibly have, and just like number each of the like indices in the array. But this method is like far simpler to implement, because you don't have to like think about all the different cases that the wall can be. And then also another thing to keep in mind is that when you're initializing the like the Manhattan distances especially, and like also the walls, make sure that you have some way to denote a blank square from the Manhattan distance of 0, or just like any Manhattan distance at all. And then also when you're initializing at the very beginning, you can assume that like the maze has walls all the way around it, and like the mouse starts at the bottom right, and that there's no walls anywhere else. But yeah, so some other tips related to C and C++. None of these really matter that much, except for maybe these 2. First of all, there's no STL library in C, which means you can't just include Q. And also there's no Boolean type in C, which most of you should already be familiar with this, because you guys have been coding the rats so far, but if you want a Boolean, just use some sort of integer to represent like the 1 or the 0. And overall, it's kind of just like a pain to program in C. But yeah, so this is kind of just like an example of how much of a pain it is to code in C compared to C++. So like all this code in C++ needs like a lot more, like you need to do a lot more for the code. So specifically for this example, something to keep in mind is that, first of all, when you use something like new in C++, you can't really use new either. There's a different, I guess, variation of new called malloc. So you would just use malloc, and if you want to free the memory, you would use the free function instead of delete in C++. If you want like more specifics, you can come up to us afterwards or when you're actually implementing it, or just like Google it. You should be able to find it pretty easily. And then also another like big difference is that in classes in C++, you can have like functions in the classes. You can't really do that in C, so you're just gonna have to pass in the struct or a pointer to the struct into like functions that are global, and just like use functions that way. Does that make sense? Okay. But yeah, you can.
Yeah. So AMC. So the date for that competition that we have been working the entire year towards is on May 26th. That's Labor Day weekend. It's a 3-day weekend, so please put that in your calendars. And return your case to the IEEE lab ASAP. If you need to put it in after this lecture, let me know and I can open the lab for you guys. And the next one.
Oh, actually, even if you guys put it in like sometime tomorrow, it should probably be fine.
That too. And then keep an eye out for these workshops. There are more to come out later, but we just want to plug it for them. And the next slide. So this is the solutions to the Floodfill code. So this link has all the Floodfill like solutions, like code wise. Use this wisely. Yeah. I'm releasing these slides anyways right after, so you guys can like take a look if you need to. And thank you. And are there any questions?
Can you go back to the start so I can sign in?
Yes. All right, that's all you guys are free to go. Thank you so much for coming to our last lecture, and good luck. Good luck with your classes. Yep.